So let's first introduce biasing, what it is. Basically, a long time ago, we started with this, a single CS stage that was biased with four sources. Four sources um, that together set the operating point at the input port and at the output port of the CS stage. During design, we assigned the values at the output port, and we did that on various grounds. For the output stage, for example, we said we are going to assign the voltage and current such that the output drive capability is sufficiently large. So for the input stage, so if this was an input stage, then we decided to choose the current such, together with the geometry, of course, of the device, that the noise was sufficiently low. So that's the output port. But of course, we cannot get the current and the voltage at the output if we don't apply anything at the input, because the transistor is a passive device and there is no reverse transfer. So the values at the input depend on what we want at the output, of course, the device characteristics, and the temperature. So if we have a different device or we have tolerances over the chip, so one device is a little bit different from another, we need other devices to have the same operating point at the output port. And of course, if the temperature changes, we need to adapt those sources such that the biasing at the output port is still stable, has still the same value. This is what biasing is about. Biasing is about designing these sources, so set the operating voltage and currents of the active devices, and of course, derive them from the power supply voltage. Because here we have studied this in the first or the second lecture already. Here we have four sources that can deliver energy if necessary, but at the end we only have the power supply. And the four sources that are shown here have to be realized with passive elements, and the currents and voltages have to come at the end from the power supply voltage. So biasing is known to be very difficult by many people. And why is that? Well, that is basically because experienced designers concurrently design the biasing and the signal path. And the tools that we have, like Spice and Cadence, don't support any other method. Because we are working there with nonlinear devices, you must have an operating point before you can do something like an AC analysis or a noise analysis. And this mixes up biasing design and the design of the signal path. And this can be very confusing if you're a novice because you're not experienced yet. So we think that it can help if you structure the whole thing, if we present the methods and the techniques in a structured way. And that is what we will try to do today. So I hope that at the end will make you a lot more happy. So let's start with the steps for biasing. The first step is that we connect the biased circuit with the four sources to a power supply. Of course, in the schematic, we draw the power supply and somehow we connect it to it. I will go through the steps in detail later on. First, I will show you a list so that you have a list that you can always use as a guidance to do the biasing of an amplifier. The second step is that we are going to redirect the current sources over the power supply. Then we are going to minimize the number of floating bias voltage source. There's a reason for that. A floating bias voltage source is a thing that should have a low impedance and that can have no parasitic impedances to the signal path, which means to the power supply. And this is very hard to realize. Everything we will make on a chip, for example, has a parasitic capacitance to the substrate. So it is really difficult to make floating bias voltage sources. Also with passive elements, we will find out that they always need some bias current to go through them to obtain the correct value. So Usually, one of the steps is to minimize the number of floating bias voltage, and I will show you later on various methods to do so. So then, of course, we have still ideal sources, and we don't want to have ideal voltage and current sources. At the end, we want to use passive devices for biasing, because the battery or the power supply is the only active device in the whole circuit, as we have seen already. So if we then have the passive elements uh, placed, then we can derive specifications for them. And those specifications should be derived from the main spec of the amplifier. And that is something that is difficult. And that often is, let's say, done in a very intuitive way. So that you don't really see the steps taken, and that someone is really considering which specs point, which performance aspects of a bias source are really relevant. So then we have a few situations. We can have situations in which the common mode voltages and currents are not well defined. I will not pay much attention to common mode biasing in this lecture, because I think differential mode biasing is already enough. I will just make remarks on that, and maybe at the last during the last lecture we can do some special topics and pay some attention to common mode biasing. So, but if the common mode bias voltages and current are not well defined, we need to define them. So we need to define those bias and currents with, for example, brute force biasing, brute force common mode in that case, just tying common mode voltages to some node with an impedance. We can do model-based common mode biasing, like we uh, can do model-based differential mode biasing, as we have discussed already. And model-based common mode biasing has been discussed in the class AB push-pull stage, where we did a model-based biasing. And we can use negative feedback common mode biasing, so measuring the common mode quantity and controlling somehow another common mode quantity at the input of the device or also at the output to get the correct value. The same we can say for differential mode. If differential mode voltages and currents are not well defined, we have the same methods. We have to define them, and we can do brute force, we can do model-based, and we can do negative feedback. But at the end, we have a little bit more techniques available. Well, we also have them for common mode, but we seldom apply them because that's not necessary. We can do auto zero and AC coupling and negative feedback biasing in this way. So let's go through the steps and do some example. And we start simple. Let's just simply start with the initially biased common source stage. So the initially biased common source stage, we have it already seen, and we are going to connect this stage to the power supply. And well, let's say that the source, which is common for the source, for the signal source and the load, will be connected to the power supply with zero impedance. It doesn't necessarily mean that it also has no DC voltage shift. So here we do it. And here I placed the device with some offset, uh, and any reason for this at this moment, of course, I don't have, because I need to complete circuit for that. But I just want to show you in general that it doesn't need to be connected to ground. You can connect it to any voltage as long as the impedance is low to the signal, from the power ground and the signal ground. The next step. Oh, sorry. And what is important here? What is important here is that all signal levels, and look, for example, at the drain voltage. The drain voltage should always stay within the power supply range. So sometimes, if you use inductors later on, it can be even outside the power supply range, exceed the positive supply. But that's why I say here, the nodal voltages should be within a valid range. So as long as it is valid in the process, you can do it, and it can exceed the power supply if valid. So then we are going to redirect the bias current sources. That was the second step. So let's do the second step. And if we redirect the bias current sources, then they go from the top to the bottom. And now you see that the current direction and the voltage drop across them can be so that they can be implemented with passive devices. Of course, we can join a few sources together. I'm sorry for the typos here. Passive and sources. I'll correct it. Um, we can take a few together. And then the next step was to minimize the number of floating voltage sources. Now, this is not really, of course, we see two floating voltage sources here, one in series with the signal source and one in series with the output. But I also want to show a situation in which it is between two stages. So here, let's say here we have two common source stages connected together with their equivalent input and output, or bias sources with their input and output bias sources, and already the current redirected over the power supply. Now there are various ways to change to eliminate floating voltage sources. One is at the, and here I do it at the input and at the output to shift them. In fact, I shifted them through the load and get a negative supply for that one. So now you see that the load is connected to some kind of common internal ground, you could say, signal ground. And the uh, input transistor, I change the voltage level of the input stage. That's what the main operation that I did there. I changed the voltage level so that also the input bias source disappears. And only one is remaining. That may be the voltage source between the two. I can do several things to eliminate the voltage source between the two. One of the things is you swap. You swap to a p-type device. You see, if you swap to a p-type device, then maybe you don't need it. But first, before we do so, I should tell you that we have still 1 degree of freedom left in our design. The output port bias was predominantly important. The current was predominantly important for that, not the voltage. As long as the transistor can handle the voltage swing there, so it doesn't go deep in the linear range where the amplification really drops, then any voltage is okay, because the drain voltage does not largely affect the behavior of the transistor, the noise, and of course the voltage drive capability. But as long as that is maintained, we can change the drain voltage. And that can be a method to eliminate this voltage also. We can just adjust the voltages such that we can eliminate and minimize the number of floating voltage sources. And that's what I also did in the next picture, basically. You see it completely gone now. And for this reason, you could say I adjusted maybe VDS of the device so that I don't need this. If you do so, you just draw in your schematic the expected voltage levels there. So you start with the power supply and the gate voltage at the P device that is now connected with the source to the plus is some VGS lower than the power supply, and that sets also the drain voltage of the first transistor. So this is one method. You replace the device with a complementary version. You should realize now, you see that in the previous picture here, everything was connected to the positive power supply by means of current sources. And if they are ideal, there is a zero transfer possible from the power supply voltage to the signal, because the current can't change of an ideal current source. So if you can make very high impedance current sources, then you can make a very good isolation from the power supply and the signal path. But if you swap the device to a P device, things become different. Now there is a path from the plus over VGS of the first transistor through VDS of the VGS of the second transistor through VDS of the first transistor. And if the output impedance of the first transistor is not infinite, and generally it is not, there is a transfer. The power supply now has become a signal source, which means that generally in this case, you you pay a price in terms of the power supply reaction ratio. Now, what we usually do is create a filter for the power supply so that high frequency changes are completely, let's say, blocked by the filter and cannot be injected into the signal path. But for low frequencies, you still have it, of course. A DC change of the voltage will cause some, will have some effect, depending on the output impedance of the first stage. Another way of dealing with or minimizing voltage sources is use a local feedback state. Now, of course, this is changing the topology of your amplifier, but as you know, a non-energic feedback stage has the same contribution, if it is current-driven CD stage, for example, to the loop gain pulse product as a CS stage. Only we are doing something with a signal inversion. So you can also say we insert such a stage in the signal path just to get what we call a level shift. The output voltage at the drain, at the source of this stage is lower than the gate voltage, so which is the drain voltage of the preceding stage. So this is also a method, inserting such a stage. And we can also do it with a common gate stage, inserting and then flipping the whole thing. And then we do it like this, and we call this a folded cascode. You know this circuit probably as a folded cascode, but it's also a way of just creating a level shift. Maybe you don't need it at all for elimination of the Miller effect in the first stage, because that was the purpose of placing a common gate stage as we have discussed it. But we want to just simplify the biasing and use a stage that folded Cascoda stage for that. So that is minimization of the number of floating voltage sources with the aid of complementary device and a local feedback device together.